Hello everyone. In this lecture, we'll be talking about power consumption in a CMOS circuit. We'll be talking about leakage and how the overall power consumption is affected by leakage and switching, and how the frequency of switching plays an active role in the total power consumption of the circuit. Before we move on to our discussion of power, at first look at some basic definitions that we have learned in our intermediate stage. The power in a circuit is actually drawn through the VDDs. Those are the power sources. Now, instantaneous power, that is power which is dependent on time, is equal to I into IT into VT. This is the basic definition of instantaneous power. Again, we have energy. E is equal to integration of 0 to infinity VT. And we have average power. Average power E is equal to 1 by T integration of 0 to infinity Pt dt. It is to be noted that P is basically 1 by T into E, that is E by T. One thing is noted: in case of instantaneous power, the power is a function of time, that is, the power changes with the time. And in case of average power and the energy, these are not functions of time, that is, these are considered for one cycle, and it does not have different values at different times. Let us look at the power consumption in different circuit elements. The circuit elements under consideration are voltage sources, resistances, and capacitance. There is no inductance involved in CMOS circuit. So in case of voltage source, we get the instantaneous power PT is equal to IT into VDD. One thing is to be noted that this VDD is not dependent on time because this is a constant voltage source. So, but the current is dependent on time. Again, now when we are considering in case of a resistance, we will get the instantaneous power is equal to I square R, IR T square R, or we'll get VR T VR square by R. By using these two equations, we will get any of the two equations, we will get the power to the circuit to the resistor. In case of the capacitance, we can measure the energy of it. Power is equal to energy by time. Energy is equal to integration of 0 to infinity I t v t dt. Now is equal to we know integration of 0 to infinity. We know the current through a capacitor is equal to C dV dt into V dt. If we integrate it, we get C integration of 0 to Vc, because the maximum voltage across the capacitor is Vc, V dt. So we will get half C Vc square. Half C Vc square is the energy consumed by a capacitor. Now, what happens in a circuit? In a circuit, when we are charging a capacitor, the output rises, and the energy since the output rises, the energy is stored in the capacitor because V out has a positive value and there is a voltage across the capacitor, and the energy is stored in capacitor. And from the previous expression, we have found out that the energy stored in a capacitor is equal to half CL VDD square. It is to be noted that in this case, when output rises, V out would be equal to VDD. V out would be equal to VDD. If V out is equal to VDD, EC becomes half CL VDD square. So this voltage source VC is replaced by VDD, and the name of the capacitor is CL. So we have CL here. But now this is the energy that the capacitor stores. Now, what is the energy that is supplied from the source? That energy which has been supplied from the source is equal to integration of IT VDD. Now, in this case, I is equal to C dVdt into VDD VT. Now, the current, because the current flows through the capacitor, we can write current as C dVdt. In this case, only one difference is there. Here, the voltage is not dependent on time. The voltage is VDD, that is, voltage is constant voltage. As a result, we bring CL and VDD out of integration, and we integrate dV from 0 to VDD. So we get CL VDD square. From this it can be noted that this energy drawn from the supply is twice the energy stored by the capacitor. So we can say that half of the energy is being stored in capacitor, and the other half will be uh, dissipated through the PMOS transistor as heat. So whatever energy we are consuming, half of it is being stored in capacitor and the other half is being dissipated through the PMOS. Now what happens when the output falls? When the output falls, this NMOS becomes active. Since this NMOS is on, the capacitor discharges through the NMOS and all the energy in the capacitor is dumped to the ground. As a result, the energy is dissipated as heat in the NMOS transistor. That is, when the output rises, half of the energy is stored in capacitor, other half of the energy is dissipated in the PMOS. When the output falls, the half of the energy that was stored in the capacitor gets dissipated into the NMOS. That is, of the total energy of the circuit, half is being consumed by PMOS and the other half is being consumed by NMOS. Now, let us look at different waveforms. So, we are considering this inverter over here. In case of inverter, this is V in and this is the corresponding V out. We can observe that there is a delay in the wave shape. There is a delay, that is, the output changes, the output doesn't rise as soon as the input falls. So this is a practical case example. When the output rises, we see half of the, when the output rises, the VDD is mapped to output. So in that case, only current flows through IP and no current flows through the NMOS. As a result, we can see when the output rises at this time, current only flows through IP. This is IP, that is, current only flows through PMOS, but no current flows through NMOS. And again, when the output falls, current only flows through NMOS, no current flows through PMOS. So at this case, when the output is falling, no current is flowing through PMOS, the current is flowing through NMOS. And if we want to measure the total, if we want to measure the current through the capacitor, what do we get? From KCL we get IC plus IN is equal to IP, or IC is equal to IP minus IN. So total current through the capacitor looks something like this. It is the subtraction of this minus this, the upper graph minus the lower graph. Again, if you are considering the power of it, power component of it, it is to be noted that when the output rises, there is current in the PMOS and there is power in the PMOS. When the output falls, there is current in the NMOS and there is power in the NMOS. If we are considering the capacitor, power through the capacitor, when the output rises, it stores half the energy, and when the output falls, it dissipates those half energies. So as a result, we get this alternative waveform. And the total power supplied by the source is the total power supplied by the source is the and here we have half to the PMOS and half to the NMOS. The summation of these two power will be total power supplied by the source, and the power will be supplied when the output rises. And if we consider the energy through the capacitor at one point, when the output rises, the energy through the capacitor rises, and when the output falls, the capacitor is discharged and the energy also falls, as we can see in this graph. But the total energy supplied by the source, when the output rises, the energy supplied by the source rises, and when the output falls, the energy remains constant. That is, no more energy is being drawn from the VDD. As a result, the energy gets a constant change. Now another power component which is under consideration is switching power. Switching power, PS, let us term it PSW. The average switching power will be 1 by T, integration of 0 to infinity IT VDD dt. Now 1 by T, we know F is equal to 1 by T. Since this is the switching time and this is the switching frequency, we name this FSW, that is the switching frequency. So we get FSW integration of C dV dt VDD dt. From there we get 0 to VDD. So from there we get the C VDD we bring out of the equation, and we already have FSW which is out of the integration. We get 0 to VDD because VDD is the maximum voltage level dV. So we get P switching is equal to C VDD square FSW. This is the switching power of the circuit. That is, our switching power not only depends on capacitance and the value of VDD, the switching power also depends on the switching frequency. That is, the faster a circuit switches. What do we mean by switching frequency? Switching frequency means how fast the input of the circuit changes or input of the inverter changes. The faster the input of the inverter changes, the more switching power will be dissipated. We do not want this power to be dissipated because this is considered as a loss. As a result, though we want high frequency operation, we have to find a way so that the switching power consumption is low. Since we cannot decrease the FSW as we want high frequency operation, what do we need to do? What we need to do is we need to somehow decrease the output capacitance of it, or we have to decrease the voltage source. And those things are used in VLSI. When we decrease, we have already learned that when we decrease the size of the transistors, the voltage requirement also decreases, and as a result, switching power is decreased somewhat. Now, there is an important factor called activity factor. What that is, activity factor is, suppose when we consider switching power as CVDD squared F, we are considering that all MOSFETs are switching at the same time. That is, if there are 10 MOSFETs, we are considering all the 10 of them are switching at the same time. But it can so happen that if in a CMOS circuit, all the 10 MOSFETs might not switch. Only a handful of them, maybe only 1 or 2 switches at any instant. At that case, if we consider this as a switching power, it won't be a correct measure of what the actual power is. So, in order to compensate for the number of MOSFETs that are being switched at a time, an activity factor is introduced. Suppose the system clock frequency is F. So, and we consider that FSW, that is the switching frequency, is equal to alpha into F, where alpha is the activity factor. Now, if the signal under consideration of which we want to measure the switching frequency, the signal is a clock, that is, it switches twice, once on and once off at every cycle. So we get alpha is equal to 1. But if the signal switches just once in a cycle, we get alpha is equal to half. That is, the total power in the switching reduces by 2 times. So depending on the value of alpha or activity factor, the total power of the switch gets modified. And this activity factor is very important because we have to keep in mind that suppose we are if we consider an inverter over here, like we have been considering so far, in one cycle of input, what would happen? The PMOS will switch 1 and the NMOS will switch once. As a result, its activity factor will be 1. But if we consider it as a NOR gate in CMOS, if we consider a circuit similar to this one, it's not necessary that all the MOSFET will turn on and off simultaneously. It may happen that the output is being changed only because this MOSFET switched on, or only because this MOSFET switched on, or this switched off. That is, each of the MOSFET has ability to keep its impact on show its impact on the output, and not all the time all the MOSFETs will switch on. So in order to compensate for it, we need an activity factor which will always be less than or equal to 1. That activity factor will compensate for the number of MOSFETs that will be switched on. We'll be learning about how to measure the activity factor in the later part of this lecture. Now, another thing into consideration is short circuit current. What is short circuit current? Suppose we are considering an inverter. So if you are considering an inverter, suppose this is our input, and if this is our input, this is supposed to be our output. This is for idealistic case, but in real case this doesn't happen. Real case, our input looks something like this, and our output would look something like this. There is a delay, that is from here we have a propagation delay. We have already learned about propagation delay in our earlier lecture. Since there is a propagation delay, at one point what will happen is, this is the circuit of inverter. At what point what will happen is, this at this point this PMOS will be on, and at this point this NMOS will also be on. So at one point of the circuit, both the PMOS and NMOS will be on, and at that point the current will directly flow from VDD to ground, and a large amount of current will flow. That current is called short circuit current. Why is it called short circuit current? Because if both the pull up and the pull down network are switched on at the same time, considering switch resistance is negligible, there is a short circuit between the VDD and the ground. So this is called short circuit current. So if both the PMOS and NMOS network are momentarily on, this creates a short circuit, and this blip of current is called short circuit current. It is a very high value of current, but for a very low time. It is less than 10% of the dynamic power if the rise or fall times are comparable for input and output. That is, if the rise time for input and the rise time for output are almost same, these short circuit current will be less than 10% of the dynamic power. But if the rise and fall times of inputs and the outputs are not same or not comparable, suppose the rise time are in 1 or 2 picoseconds, and the fall time rise time of the input is 1 or 2 picoseconds, and that of output is 10 or 15 picoseconds, then they are not comparable, and at that time the dynamic power consumption for the short circuit current is very high. And we generally, what we do is, in idealistic condition there is no short circuit current, so we generally ignore this component, because we design the circuit in such a way that the rise and fall times of input and output are generally comparable, and as a result this total short circuit current or short circuit power is less than 10% of the dynamic power, and since its value is very low, we can sometimes ignore this, and we generally do ignore this short circuit current. Now, power dissipation, we have two types of power dissipations under consideration. Firstly, dynamic power, which we have studied so far. Dynamic power contains two components, switching component and short circuit components. Dynamic power is the power consumed when there is a change in state, that is, when the input changes or the output changes. What we have, the power consumption at this time, this is called dynamic power. That is, at the change of input or output, the change in power is called dynamic power. So two types of dynamic power we have already learned about, switching power and short circuit power. Another power is important, which is called static power. This is the power which is being consumed by the circuit at all times. This static power is generally created by leakages and the parasitic components of it. For example, we know that no current, in case of a MOSFET, the gate is insulated, that is, no current should go through the gate. But in real life, some current goes through the gate, as this is called gate leakage. Similarly, there are subthreshold leakage, junction leakage, and contention current. These all current create power loss, which is called static power loss. These all current, when multiplied by VDD, we get our static power loss. So we have two types of power, dynamic and static, and the total power will be the sum of dynamic and static components of power. That's all for this lecture. In the next lecture, we'll be learning about dynamic power consumption in detail and how we can reduce the dynamic power consumption.